Hello there. A couple of weeks ago, I was watching a video made by Core Electronics, and it was on hooking up the new Raspberry Pi Pico to a string of WS2812 LEDs and getting that to work with the new PIO programming capability that the Pico has available for it. I have done projects in the past where I use SK6812 LEDs in place of the WS2812s because they're RGBW LEDs as opposed to RGB LEDs. It has a dedicated white channel that is a lot nicer and cleaner than the white that is generated by turning on all three colors at once to simulate a white color. So I asked in the comments if anybody had gotten an RGBW LED to work, and nobody had, but there was some interest in seeing if I could get that, or if anybody could get that to work. And I was planning to try as soon as I got a Pico in. One of the users, JCUELLAR578, asked that if I ever got that working, that I would post the results of that. Well, I got my Pico in, and after a lot of work, it wasn't really a lot of work, after a little work and a lot of hunting on the internet, I finally managed to figure out the few changes that is necessary to get an RGB WLED to work. And that's what this video is about. So let me take you over and show you first what my current Pico configuration looks like, and then I'll take you into the code of the original and the modified so you can see what it takes to make an RGBW LED work. Here is my Raspberry Pi Pico and its exquisitely simple hardware configuration. I have attached a connector to pin, I think that's pin 20. Whatever pin I was using as my output pin, I think it's pin 20, and ground. So the white wire is ground, the green wire is signal, and the red wire is power, but I am not taking power off of this Raspberry Pi board. I am using 5-volt power directly off of another USB port. And the way my LED strings are configured, I have an input connector and an output connector on the string. So I'm injecting the power at the output connector at the end of the string and injecting the signal at the input connector at the beginning of the string. And I have an RGB WS2812 string and an RGBW WS6812 string, or SK6812 string, excuse me, both with the same kind of configuration. So you'll be able to see both of them and see how they work. So anyway, that's the setup. I'll bring you to the original code that was used with the 2812. Now I modified the code a little bit from what Core Electronics used in their demonstration, and I'll show that to you and I'll explain why when I get the code up. So I found the code that I am using at this website right here, and it is almost identical to the code that Core Electronics was using in their display. Their code had a color wheel rainbow kind of effect that was running on the LEDs. Unfortunately, that doesn't work really good for showing an RGBW LED because there isn't any white used in that color wheel. So the original core example, and by the way, this core example actually comes from the data sheets that is put out with the 2040 chip. So it's, everybody is kind of starting off and modifying that bit of code because it has the PIO programming in it to drive the LEDs already done for you. So a lot of people have been using this, and I'm not going to rock the boat at all. I'm going to continue to use it. But if you watch Core Electronics video, you've already seen him talk through most of this. I've simplified the code a little bit. To start off with, the pixel show routine had a brightness control feature built into it where they took each pixel, multiplied it by the brightness, and then stored it back away. Since you add more bytes of value with the RGBW, that routine would have had to been changed in order to do RGBW, and I didn't want to mess with that. So I just show the full brightness thing, and that doesn't take any calculation at all. It's just a matter of putting it out to the PIO program. So the other thing I did was there used to be a single instruction routine that had this line in it, and this function just called that one line routine. I saw that as a waste of a lot of stuff, and I just moved that line into this code. So instead of two functions here, the pixel fill function just does the pixel fill. So in this program, you have the code up here that kind of does the work. You have a definition. I think they call these tuples or something like that in Python, but it's just a definition of the different colors as 3 byte values in a sort of array. And then they define the list, I guess this is, of colors in this order. And then the simple routine just says, for each of the colors in color, fill the array with that color, show that array, sleep for a second, and then go on and do it again. So it's very simple. So it's going to step through these 8 colors, if you want to call black a color, and then it stops. That's the whole program. And so I'm going to take you to my handheld phone to actually video this running because I don't have a webcam that can shine down on where I have this set up right now. So I am going to hit run on this, and then I will switch over to my other camera and show you that video. So here we are cycling through each of the colors in that colors list. Now the white that's in here is going to be made by turning on all the colors at once. And it's a little blown out, so let's try it with a paper over it. There you go. So it's a little bit easier to see maybe. But again, the white there, all 3 colors. That's it. That was a 50 string LED. I wrapped it around a tissue paper tube and stuck the extra LEDs inside the tube just to have a way that I could keep it kind of compact so I could show it to you, because I don't have a nice array of LEDs at my disposal. I just have these long loose strings. So now I'm going to take you to the modifications I've made to make this work with the 6812 with this exact same set of code. So I just flip over to that, and the first thing you need to change is where you are defining the PIO assembly language code. You have to change the pull threshold from 24 to 32. So there are 24 bits of data that need to be pulled in for an RGB color. There are 32 bits that need to be pulled in for an RGBW. Nothing else changes in the entire code. The timing's the same. The timing between high and low bits, which is all that's done by these wait states, is all the same. So nothing needs to be changed other than the number of bits it's going to take. So I did change the name. That wasn't necessary. But because I'm doing this for a SK6812. By the way, I do believe there are WS2812s with RGBW also, but I can't really find those. And there are SK6812s with only RGB or just white. So there's a lot of different variants. So the name of the display itself really doesn't tell you how many bits there are, but you know, just cause. I use the SK6812s for 24-bit or for 32-bit, and the 2812s for 24-bit. So in the setting up of the state machine, there is no change other than that name change, as I mentioned. You activate it the same way. You set up an array of LEDs the exact same way. When it comes to doing the show, I didn't point this out, but let me pop back over here. The show for the array has this condition that says 8. And I've done a lot of research trying to figure out exactly what that means and where it's defined, and I haven't been able to find that. But I did find some comments about it tells it to take 8 bits at a time to send out. So it's like pushing to the FIFO or whatever inputs it into the PIO 8 bits at a time, because there's no even divisible by a power of 2 for 24 bits. So you do 8, 8, and 8, and then you do the next one, 8, 8, and 8. For the 6812, you need to send out 32 bits, which would seem like, well, if you're sending out 8, 8 ought to work there, but it doesn't. 8 does not work there. It has to be set to 0. So that's the second change. So you have to change the 8 to a 0 to get it to take all 32 bits. I also commented out the sleep because I didn't think it was necessary, and it didn't seem to make any difference. Every bit of code I've seen has this 10 millisecond sleep thing in it, as if there's some kind of race condition or something they're allowing to settle. But because my show routine has a 1 second sleep in it already, I didn't think it was necessary to have another 10 millisecond sleep. So I just commented it out. Okay, the next thing you have to change is now you need to have 4 bytes. So in the original sequence, from high to low, you had the colors defined as RGB. When they actually go out to the string, they have to swap the bit orders because they're actually GRB instead of RGB. So this, let me go back to the WS2812 just to show you that it's in here. Originally in this code, they took, so they're taking the colors from this RGB defined tuple of data, and they're picking out the data. So they have to get the colors in the right order, and they do that here in this pixel fill area. So they start off with the first color value, or the color value in position 1. So this is 0, 1. This is RGB, so that's G, and they shift it over 16 bits. So they put it in the highest bit location. Then they take 0, R, and they shift it over 8 bits. So it's GR, and then they finally take the blue and they put it in the last position. And so that's how they reorder it to send it out to the string. So on the 6812, you have to do the same thing, except now you're going to have 32 bits and you have to add the white byte of information in there. because now you have RGBW defined in the tuple instead of RGB. The first three colors are exactly the same. They're just shifted over an extra byte to get them up in the high order area of the word that you're going to be sending out. And then you add the third color, which is the white color on the end. So that's the third change you have to make. And that's really all the changes to the code you have to do. But you do have to define your values now as 32-bit values as opposed to 24-bit values by adding the extra 0 in the tuple to include that white definition. And lastly, the last thing that's changed is now that you have a white defined, when you want to turn on the white color, you actually activate that white pixel as opposed to activating all three of the colored pixels in the RGB code. And that's it. And the rest of it is the same. So let me swap out my strips and I will show you that and show you how it works. Okay, here's a panel of RGBW LEDs. If I can get close enough and keep my focus, you might be able to see that there's a big focus. Come on, you can do it. Let me back up a little bit. You can see there's a splotch of yellow on one side of the LED, and that is the white half of the LED. So the colors are on one half and the white is in the other half. And that's the way you can tell that there's a white element in there, because they use a phosphor coating on the lens with, I believe, a blue LED underneath it to create the white color. And it's the doping of the phosphor that gives you the exact color of white light that you're going to get. So if it's going to be warm white or daylight white or natural white, will be depending on how the phosphor is doped and not how the LED is doped. These are what's called natural white, which is kind of halfway between warm white and daylight white. And it, to us, most accurately captures the color of an incandescent bright white light bulb, which is what we were going after when we were looking at these LEDs. Let me hit run on my code, and you will see this step through the different colors. Okay, look just like the other one, and you notice the white on the end looked kind of just like the other one. Let me put a piece of paper over that to mute those colors so it's a little bit easier for the camera to see. And run it one more time. And there you go. So that's it for what it takes to modify the code so that you can get a basic RGBW LED to work on a Raspberry Pi Pico. It's really not much off of the given code that's in the data books and stuff like that. Just a few minor changes and it works really, really well. I do want to take a little bit of time to show you a more enhanced RGBW program that I have been working on since I got this working, just to kind of show you, what you can potentially do with it. I have not still put in the rainbow code that was in Core Electronics' original video. I do want to add that to mine, but it's not in there yet. But I will. So let me bring this code up and I'll show it to you. Okay, here is my latest code. I put another acknowledgement in here because I've taken some of the stuff that's in this code from a raspberrypi.org website. So I wanted to just give them credit that I picked up some information. I didn't copy their stuff verbatim, but I did use their ideas in this code. So to start off with, the first thing I did was I added a gamma correction table, kind of a modified gamma correction table to this code. For anybody who's worked with LEDs for a while, you'll know that they're not really very linear as far as the human eye is concerned with their brightness levels. So the changes in the dim values are drastically more noticeable than the changes in the bright values. So the normal gamma tables that are out there that you can find will typically have like the first 27 locations are all zero. So anything that low just doesn't show up at all. I wanted my gamma table to only have one off condition and one full brightness condition, and then the gamma would be adjusted in between that. So I rescaled the gamma table to make that fit by adding one to each location. It wasn't a hard job to do. But this does a pretty good job of making it look more linear. So if you say 128 for a brightness value, it looks close. It looks close to 128. 128 is half as bright as 256 is, or 255 is. It doesn't go 256. So anyway, I added that gamma table, and I put back the intensity control capability that was in the original code that Core Electronics had, except I take whatever is calculated by doing the brightness adjustment and multiply, or I pick the gamma equivalent out of that gamma table to display as opposed to the original one. The other thing I changed is they just hard-coded a brightness value up in the definitions at the top, like a global variable that told you what the overall brightness was going to be. I changed that to be a value you pass in right here with a default of 1. So if you don't pass a brightness value in, it will give you full brightness automatically. If you give some value less than 1, it will use that as a scalar to scale the brightness of the LED down to that brightness. So you can use routines that want full brightness, or you can use routines that want whatever brightness you want to be adjusted. The rest of this stuff is pretty much what was in the simple code. And then I added my routines that are going to do the displays. So I have a routine that uses a tuple definition for color and fills the whole array with that color. So that's similar to what we were watching earlier. I also made a routine that will take an integer value for the color, so a 32-bit unsigned integer as the color value, and it'll fill with that color value. So the only difference in these two is the color fill tuple takes the data out of each of the tuple bytes and shifts it over and creates a 32-bit word out of it and puts that in the array, where the fill int just takes the passed in integer and puts it directly in the array. So, so I have those two fill capabilities. I made a color wipe routine, and what the color wipe routine does, it takes a tuple in along with a weight value, and it displays one LED, waits, then displays the next LED, and so on and so forth on down the line. It does its own put So it does not use the brightness scale put capability. It is just putting out the full intensity of the LED, or it's putting out whatever you give it as the number. So you can scale it before you give it to it if you wanted a lower value than full. Then I did a color change RGB routine. So what this will do is it will take an initial value. You have to give either an R, a G, or a B, but not all of them, because if you put all of them in, it'll be white, and it'll shift them around, but they'll stay white. So if you put a value in R, it'll display a red for the first amount of time. Then it will shift that to a different color, like say green, and it'll display green for a time, and then it'll display blue for a time, and it'll come out back and it'll display red for a time, and each time it changes. Now this uses a millisecond style counter to determine how long to display, so there are no waits in here. And this came out of another routine that I used where I did not want any waits in my program because I was doing other stuff in the background on another type of processor, and I just kept the code the same. So what you do is you set a speed between 8 and 11, and the higher the number, the lower the speed of the, I think. So anyway, what it does is it takes the millisecond counter, shifts it over that number of bits. So the more it shifts it, the more higher order bits of the number you're getting. And then it divides that by 3 and takes the remainder and uses the remainder to determine what color mode we're in. And it'll do a shift depending on what color mode we are in. So if we're in time 1, we shift a particular way. If we're in time 2, we shift a different way. If we're in time 3, we shift a different way. And then we return that value. And then I made an RGBW equivalent of that same routine. So I added the W as an input value, and I just had to do one more shift. I had to divide by 4 instead of 3 to give me remainders between 0 and 3, and then I use that to pick how to shift them. One of the last routines I made was the thing I call a sign sweep tuple. So it takes a tuple color, a size, which is a division of your overall array. So it's going to create a sine wave type pattern in the intensity. So it's going to start with a low intensity, get brighter and brighter and brighter and brighter, and then lower, 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 lower. The size tells you it's an integer number, but it tells you how big you're going to make the sine wave in comparison to the overall LED matrix. So if your LED matrix is 50 and you put a 2 in here, it'll be half of 50, or 25 LEDs will be in the sweeping pattern. You can use 0.5 and get the sweeping pattern to be twice as big as the LED matrix you have. Now, a word of warning on this: it is not a very efficient piece of code because it creates an array as big as your defined sine wave. So if you had 200 LEDs and they're 32-bit numbers, and you create, say, a sine wave that's 5 times that, then you're going to be using 1,000 times 32 bits worth of buffer just to hold the sine wave definition in. So it could use some cleaning up and some um, whatever, but it works. It's just a concept. So I wanted to see how that would look and what it would be like. And then I have my same color definitions as before. And then I run through each of these code things. Now they actually look a lot alike. There are different ways to produce different things. Uh, so, so let me start right up here. The first thing I'm going to do is I'm going to do a sine sweep of green that's divided by 0.5, so that's twice as big as the original array. Then I'm going to do a red sweep that's 1/4 of the array. A sine sweep in blue that's 1/6, and a sine sweep in red that's 1/8. And then I'm going to pause for a second. And then I'm going to go into the color wipe tuple, and all that is a fill in, one LED at a time. And I'm going to do that in red and green. And then I'm going to do the pixel fill. This is where it fills everything at once with a brightness and then without the brightness, just to show you the difference. And I'm doing approximately 0.3, which is about a third. So it'll be about a third brightness. And remember, these are gamma corrected brightnesses. And then I will go through the pixel change color, running slow at 11 and then running fast at 8, just so you can see that. And then I'll do a plain old color wipe with red. So I'm checking out each of these machines. I don't think I'm going to mute these. I'm just going to record the different steps so you can see them. This is hard to hold the camera and hit the start button at the same time. Okay, so there's a sine wave scan, so you can see how it fades up. And there it is in littler bits. It looks really better if it's really big. Now this is the wipe, the color wipe. This is the dim and the bright fill in red, dim and bright in green, dim and bright in blue. And then I think it goes yellow. That looks like white to me. That's white. Now yellow. Blue. And that was cyan, purple. The next one's purple. And then it'll go to black. And black. Okay, so this is the RGB change color. RGBW, I'm sorry, change color. This is the RGB change color with a very low intensity. I don't know if you can even see that it's on. And then finally a red color wipe, and that ends the routine. So that just shows you some of the capabilities that these LEDs have, and hopefully you will be able to use some of this code somewhere in your programming of this little Pico. So my next adventure is going to be into how well the interrupts work, because if I'm going to use this as a replacement for the STM32 blue pill that I'm currently using, I need to be able to handle 6 simultaneous external interrupts and differentiate between which pins did the interrupts. because that's how I input my data currently. Actually, this chip is probably fast enough that I could do that. You know, I could use a second core to just scan those inputs and do it with plenty of time without using interrupts at all, which is a possibility. I might play around with that. So anyway, I'm having fun. I hope you guys are. I should be looking at the camera and not at myself on the screen. I'm having fun. I hope you guys are having fun. It's great learning about this thing. I can't wait for more documentation to get out in the field. The one thing about this rapid release of this Pico is that it's going to take a while for the community to generate information that people can use. So I hope somebody out there finds this usable. Thanks a lot for watching, guys.